great to be here. And it's actually very sunny in Poland and much warmer than in Turkey, so it's surprising. So our focus today is Solana engineering case study on compatibility. And what does it mean for us as Solana community? It means that we'll explore how we build Neon, which is not another bridge or another layer, but it's fully integrated Solana program. The case study resolves around entirety of Solana architecture. So entirety of Solana architecture to host and execute bytecode from Ethereum natively while preserving all of the core principles of Solana. And to be fair, that was the end of intro that I wanted to do, but there's also one more thing that I will be talking today, and it's going to be mentioned for the very first time, because Neon EVM is the first network extension that we are working on, but there is also another concept that we are exploring that targets SVM builders only, and it's a concept of light transactions, something that I'll discuss later on, but something that aims to basically remove all of the core limitations of Solana. But let's start with what Neon is. To be precise, from Solana perspective, Neon is fundamentally a Solana program. It lives entirely on stage, and it's like any other program you may have built or interacted with. Its function is unique, though, because it contains interpreter that is capable of executing EVM bytecode. So you can think of it as enabling Solana to run and understand instructions from different environments. And because it is a Solana program, it has a couple of advantages. For example, interactions are paid for using Sol for transaction fees, including priority fee that is used to navigate through network congestion, just like any other native Solana interaction. Executions consumes compute units, and also Neon program makes direct use of native Solana syscalls for essential functions. So how did we architect this to work efficiently on Solana? There are basically two components. The first one is Neon program, which lives on chain. It's built in Rust and compiles to BPF, and you can think of it as heart of the system. The interpreter deployed on Solana that executes EVM logic. And second, critical, is Neon proxy. And why is it needed? Because as we all know, the Solana's runtime environment requires all transactions to declare all access accounts upfront, which for the safe parallelization. And EVM transactions don't inherently provide this. So Neon proxy acts as a pre-processing step for Solana. It accepts EVM transaction. It accepts EVM transaction, simulates the entire execution path off-chain to identify all of those accounts that Neon program will have to read from or write to. It then constructs the normal native Solana transaction that is then being sent to a Neon program. And all of those transactions are like any other native Solana transactions. They can be scheduled, they can be even parallelized. So in a sense, we are building, and why I'm saying all of this is because I want to highlight that we are building for the Solana architecture and no against it. So let's delve deeper into this critical translation, solving the state access problem. And as we all know, the high-performance C-level requires all of the accounts to be declared up front, and EVM logic is kind of different because it allows to declare which contract or storage to access during the runtime. And it wouldn't be surprising if I told you that we actually managed to solve this minor inconvenience, because otherwise I wouldn't be standing here. And the key here is the Neon proxy. Before submitting anything to Solana network, it identifies every single transaction that will have to be touched by the Neon program. So this includes accounts holding contract code, EVM storage slots, balances, and so on. It then creates this list of public keys of those accounts and sends it to Neon program. So in essence, what we were able to do is we were able to engineer our way to run a dynamic EVM logic directly in static dependency Solana model. But it wasn't only about account limitations that we had to engineer for. There is priority fee limitation, which is kind of critical for Solana. And the thing is that Neon proxy doesn't just pass on the default fee. It employs some adaptive algorithms that are used to monitor the network and set the appropriate priority fee that helps transactions that are then being processed by Neon program to have rather highly chance of timely inclusion during the network congestion. We have compute units management, which is another core limitation for Solana. So the thing is that Neon proxy provides rather highly accurate compute units estimations, which helps to limit failed transactions and, in the essence, to increase the user experience. But we also tackled another interesting problem, which is large EVM operations, because there are EVM operations that are essentially too big for Solana to handle. And how we did this is we implemented iterative execution that breaks the entire EVM transaction into small transactions that can be fit within per transaction limit on Solana network. It basically breaks the large operation to smaller transactions and then executes them as a sequence. There is on-chain logic to ensure about the atomicity of the entire sequence, meaning that if either of the transactions fail, the entire sequence is rolled back to preserve the expected behavior. And what we can do with that, there are a couple of interesting applications, but the one that I wanted to mention is ZK proofs, because building ZK proof verifier is kind of a complex task if we want to do it natively in Rust and Solana. It's complex from the perspective of compute units budget, but it's also complex from the perspective of cryptography itself and optimizations. So Neon can act as a step to enable to use those ZK verifiers, because as we may or may not like it, EVM does have some battle-tested, mature, and audited ZK verifiers that are solidity-based. So the Solana program that requires to verify a proof could just make a standard CPI call to the Neon program, specify the address of the pre-deployed Solidity contract. Then Neon program can just execute the entire logic and pass on the data from the Solidity ZK verifier to the calling program via the standard CPI. So in essence, even though it's Neon is EVM, it still enables Solana users to leverage the work that is already available. So to recap quickly, the thing that I was discussing, so Neon EVM is our first network extension. And I want to highlight that it's not another bridge or another layer, so we are indeed native. But there's also another concept that we are exploring, and this is something that targets SVM builders only. So to recap quickly what issues Solana has in terms of limitations. There is limited computational resources, obviously, which doesn't help when we want to execute large operations automatically on chain. And often those operations have to ensure about the atomicity, we have to move those operations off chain to another layers. Which adds to complexity, but it also adds to security risks because there could be some additional potential attack vectors. Then we have CPI and stack limitations. As we all know, CPI, we have 1.4 compute units limit and 4 nested stacks at the maximum, which doesn't help with advanced DeFi strategies. On top of that, we have high priority fee, especially during network congestion, which doesn't help when you have to pay several sol just to get the transaction through. And the network congestion itself, when you have many transactions that fail, then it limits user experience and engagement. So our idea is pretty simple to describe, but it has pretty solid advantages. The idea is that instead of using standard RPC, application or user could just send the transaction to the specialized RPC that supports this light transactions concept. The RPC then handles things differently because it fetches minimal required data. It then spins the separate SVM, executes the entire logic without any limitations from the computational unit's perspective, and only gives back the resulting state. So in essence, it basically allows us to launch large operations atomically natively to Solana without using any other rollups layers or any other bridges. It also allows us to completely negate the limitation from the computational power. It can also help to reduce priority fees rather heavily, especially during network congestion. That could then lead to very much higher user experience. It also ensures about no third-party delegations because it's still staying native to Solana, and it preserves Solana's high-performance transaction fees. So that's like a summary of the entire concept, and I'm running a little bit out of time, so I would be happy to connect to everyone that is interested to learn or learn more or just to talk, either about that or about trading meme coins, but because that's also interesting. So thank you very much for today. I would be happy to connect with everyone that wants to hear more about what we do. And yeah, that's it.